And this is another good news for the day. We still have time for one video actually. So let's go for next chapter, multiple integrals. Okay, well, first part multiple integral, and then we'll talk about line integral after this. Okay, so let's start with some very simple things which should be reminders of what you saw last year. Okay, so we're going to talk about multiple integrals for functions of n variables, but n is most of the times going to be 2 or 3. Okay, so let's talk about some simple cases. First simple case, the rectangle with 2 variables. So you've got a nice area of the R2 plane that will be defined by, well, let's say that X is between A and B and Y is between C and D. Okay, and so this nice area is going to be defined like this, and we want to talk about all the x, our domain of integration are going to be all the xy's that belong to this rectangle. Okay, so for this you have the Fibini theorem, that for this kind of simple cases you have the Fibini theorem that allows you, it's not reminded here, but that's very important. The Fibini theorem allows you to exchange the order of integration provided that the function is continuous. Okay, if that works, if f is continuous. Okay, and that may be a good occasion to start with a nice counterexample of Fibini. Okay, all right, so next, let's call that a counter example of Fibini. Right, let's work with the function x2 minus y2 divided by x2 plus y squared to the square. And let's perform this integration, dx dy. Let's perform this integration on a nice square between -1 and 1. That's the nicest square you could expect. Okay, so that's the one, right? -1, 1, -1, 1. Okay, but maybe as I've just told you, we should check for continuity. You see that we may have a problem in 0 because, well, 0 does not belong to the domain of the function. But you remember that we studied some continuous extensions that may happen. It depends on the case, right? So, but let's be naive and perform the integration as is. Okay, so we can see that this function actually can be seen as on one side. I will let you do the calculations, but you can see that as d over dy of function defined by y over x2 plus y2. So maybe you can take some time to recalculate that derivative to see that you find indeed that stuff. Okay, or can be seen as d over dx of minus x over x2 plus y2. Okay, again, perform the derivative of these two functions and see that it gives you actually the functions you're looking for. So let's perform this integration. So we've got, let's call this I as integral. I is equal, if I keep my order by dx dy first, dx first and then dy, I will get that it's going to be the integral of -1, 1, so I am keeping the dy, and the dx tells me that, well, that's going to be the primitive of this function as a function of x, so that would be minus x over x2 plus y2, and this between -1 and +1, right? So that's giving me integral between -1 and 1 of -1 over x2 1 sorry, that's the x I'm substituting. So minus 1 over 1 plus y2 minus 1. So minus, and then we have three minuses, so in the end it gives me another minus 1. So let's make this minus 2 over 1 plus y2, and what's remaining is the dy. Now I just have to integrate this, maybe put the negative 2 outside of this integral, and that's just the primitive of 1 over 1 plus y squared. And this, my friends, this is one of the primitive that you have to spot very directly. What is the antiderivative of 1 over 1 plus x squared? That's the arctangent. Okay, what I mean by arctangent, you can call that tan minus 1, but it's the inverse function of the tangent. By this, I mean the tangent takes anything, well, if you want this to be a nice invertible function, which is what we are looking for. So the tangent looks like this. We have to restrict that to negative pi over 2 to plus pi over 2. Okay, let's try to get rid of that. I don't know why. Okay, anyway, and so it goes from negative pi over 2 plus pi over 2 excluded to r. Okay, it goes from negative infinity to plus infinity. And the arctangent does the contrary. It goes from r to minus pi over 2 plus pi over 2. And if you can spot that, that's if you want to draw it, it's very nicely drawn as, well, you just have, if you want to draw it on the same, probably my last draw is not very nice, something like this. Okay, so that's going to be arctangent, and it has some horizontal asymptotes in plus and minus infinity that are going to minus pi over 2 and plus pi over 2 here. Okay, so that was just a side note, and something that's such a convenient function that we use for tests that you really have to know this one by heart. Okay, so back to our double integral. If I do the integration with respect to x first, which I was doing, I get the arctangent of y, so for 1 and negative 1. Okay, and of course, you know that's going to be, well, arctangent of 1 is just pi over 4, minus the arctangent of negative 1, which is so minus pi over 4, minus, so plus pi over 4. Okay, so I've got 2 pi over 4 times negative 2, that's negative pi. Whereas if you perform this integration, let's call that I tilde as negative 1, 1, negative 1, 1, my function, but dy dx, guess what we're going to get? So we get the integral between negative 1 and 1. So first primitive that I'm going to write is the one related to the y. So y over x2 plus y2 to negative 1 and 1. Dx is remaining. And so it's nearly the same stuff as before, except that I don't have the minus in front of it. So maybe you can just pause and do the calculations. Okay, you should find plus pi. Okay, so here we had a function that seemed quite okay on a very nice square, and the results were opposite depending whether we were doing the integration with respect to x first or to y first. Okay, what was to blame here? The function is not continuous somewhere in the middle of that domain, and that's the point 0, 0. And for this, again, prove that it's not continuous in 0. maybe use polar coordinates. That seems an excellent idea here. Okay, this being said, so that was a counterexample, so that you shouldn't use Fibini's theorem without checking first that your function is indeed continuous everywhere. Okay, so maybe we still have time for one or two nice and simple examples that are telling you, well, what comes next is that, okay, that square is the easiest case. But now if you have something a bit more complicated, like something looking like this, meaning that for x belongs to AB, we have y between two functions of x. So let me change to a finer one. So let's assume didn't work. Let's assume this is x, this is y, and now I'm going to define two nice curves. Let's call that, according to my notation, psi1 of x, psi2 of x, and AB. Okay, you see, now we don't have anymore an I square, we've got something more complicated, but in that case, it's still doable, all right? As long as you can still adapt the, well, you can still compute the integration, and maybe if everything goes fine, you can exchange the order of integration. Okay, so that last case, there is a big warning. You should, if needed, adapt the bounds to anything consistent. Let's do one of those nice, very nice example. Okay, so let's do this one. Let me consider the domain of R2 that is going to be defined. So that's x, that's y, and I'm plotting here the parabola y is equal to x squared. And I want actually to be on this domain. Okay, this domain with x is equal to 1, right? So below the parabola and between the x-axis and the parabola, how can you describe this domain? That's going to be one of the most important things, actually, when you want to, usually in exercises, I will describe you some domains by saying it's below the parabola and above x-axis. Well, I may tell you this kind of thing, but maybe I would be more precise. And x is between 0 and 1, right? And that's my domain of integration, and I want to integrate on this domain the one function. Okay, that's the kind of thing I can ask you. And maybe you have learned last year that if I integrate the constant one function gives me the area of the corresponding domain. But anyway, we'll talk about that later on. So one way to do that is to say, well, how do I describe this domain? Y is going to be obviously bigger than 0, but smaller than x2. And x, in that case, should be between 0 and 1. So in that case, if that's the description you get, you don't have the choice for the order of integration. As y depends on x, well, you must integrate with respect to y first. So that's what you're going to get. 1 dy dx, and that's going to be 0, 1. Well, sorry, 1 between 0 and x2. Dx, sorry, and that's just going to be integral between 0 and 1 of x2 dx. So that's 1 over 3 of x3, so it's 1 in 1 and 0 in 0. Whereas if you do it the other way around, if you want to integrate with respect to x first and then to y, well, you have to consider how to express these variables as in order to be able to exchange this order of integration. You wouldn't be able to exchange it directly. You would probably need to say that x is smaller than 1 but bigger than square root of y, and y then should belong to 0, 1. Okay, so now it's your go to try to finish that and show that you get the same value in the end doing this order. but then you see exchanging